The last time we ended up with the standard model. Okay, then let's continue from last time. The last time we ended up with the standard model gauge fixing term in RxI gauge. Remember that RxI gauge is a special gauge fixing which is very practical and very often used in concrete calculations at tree level and at higher orders in the electroweak standard model. It is adapted to loop calculations in particular because certain mixing terms which mix Goldstone bosons and gauge bosons which appear otherwise in the Lagrangian are simply cancelled by a tricky choice of the gauge fixing where you have basically squares of this gauge fixing function which combines derivatives of gauge bosons with Goldstone bosons, and those cancel similar mixing terms from the kinetic terms of the scalar fields. And what just remains to do is to say what we already said in the generic case for a general Young-Mills theory with spontaneous symmetry breaking, namely the gauge fixing term cannot come alone on its own. It must be accompanied by Faddeev-Popov-Ghost interaction terms, because only then the full Lagrangian has a symmetry, BRST symmetry, which guarantees that then the physical S matrix is unitary on the subspace of physical states which have positive norm. And so how can we extend the gauge fixing term to a BRST invariant Lagrangian including Faddeev-Popov-Ghosts? Very simple, exactly copying the generic situation. So let's extend it to BRST invariant L fix plus ghost, namely by writing the gauge fixing plus ghost term as a total BRST transformation of something else. So we have to apply the BRST operator S onto something such that when we choose something appropriate here, this construction leads on the one hand the gauge fixing term that we want plus something else, and the something else will then be the necessary Faddeev-Popov-Ghost interactions. And so here we simply can write the anti-ghosts C bar I, let's say, where I is summed over the four possibilities here, times psi I over 2 times bi plus fi. And if we evaluate this, let me just check, if we evaluate this, then we obtain on the one hand quadratic terms for the b's. B's can be eliminated. And then we obtain from this construction L fix plus ghost is, if the b's are eliminated, gives the previous gauge fixing term plus a Faddeev-Popov-Ghost term, and the Faddeev-Popov-Ghost term has the form which you obtain by acting with the BRST operator on the round bracket. So it gives minus the anti-ghosts C bar I times the BRST transformations of these FIs, where the FIs are the ones that you want in the gauge fixing term. So, and here at this point in the lecture we do not work out all the calculational details for this, but clearly this can be worked out because everything is completely fixed, everything is completely unambiguously determined by the definitions that we gave, and therefore what you obtain from this is clear. It just needs to be calculated, and then you have certain Feynman rules for the Faddeev-Popov-Ghosts which are necessary in the loops in order to make the physical S matrix unitary. And let me just give you some examples. What are some example terms? So from evaluating this, for example, if we look at the BRST transformation of this gauge fixing term involving the W plus. What do we obtain if we apply a BRST transformation onto such a term? The BRST transformation of a gauge boson is the covariant derivative of the Faddeev-Popov ghost. So from this term we on the one hand obtain d mu times the covariant derivative of a ghost, which is on the one hand the normal derivative of a ghost, d mu c plus, times gauge coupling times structure constants times products of W's and ghosts. So let me just write proportional here such that you can see the structure. You get gauge coupling times a product of W bosons and Faddeev-Popov ghosts. And therefore, plugging it into the Lagrangian, so this was from the W boson, and then from the Goldstone boson, we know that the Goldstone bosons transform into the ordinary Higgs field times Faddeev-Popov ghost, so we get plus MW times zeta W times terms proportional to vacuum expectation value plus Higgs field, also in this round bracket. Outside of the round bracket. So this is the BRST transformation structure of this term. And so therefore, if you look at the terms in this ghost Lagrangian, it contains the following terms. On the one hand, it contains anti-ghost times double derivative of a ghost, which is something like this, C bar D'Alembert C, which is a kinetic term for a Faddeev-Popov ghost, and it comes with a minus sign such that it has the ordinary sign of a kinetic term for a scalar field, and that will lead to a scalar field propagator for the Faddeev-Popov ghosts. On the other hand, from this term here, you get plus a constant MW times zeta times vacuum expectation value, and this in the end boils down to MW square times zeta times products of Faddeev-Popov ghosts. So this is like a mass term of the Faddeev-Popov ghost, and the mass is correlated with the mass of the actual gauge bosons up to the gauge fixing parameter zeta. So looking at these two terms, the Faddeev-Popov ghosts act like scalar fields with a mass, and the mass is MW up to the factor zeta. Okay, and then there are interaction terms. So here you have a term of the anti-ghost multiplied with the ghost and the Higgs field. So this gives an interaction C bar Higgs field times the ghost multiplied with the W mass and with the appropriate zeta factor. So you have an interaction of the Faddeev-Popov ghost with the Higgs field, and from here you have an interaction of the Faddeev-Popov ghost with the gauge field. So, and as I said, the prefactors are unambiguous, but we do not work them out now. At some point I will give you the Feynman rules in detailed form with all the prefactors, but here I want you just to understand the structure and to understand the mechanism where it comes from. So the comment is that the Faddeev-Popov ghosts act like fermionic scalar fields. So they have the wrong statistics. Scalar fields with a mass given by the corresponding psi or zeta times the appropriate W or Z boson mass square, depending on which ghost you are looking at. And there are interactions of the following form. On the one hand, we have an interaction of the Higgs field with ghosts and anti-ghosts, and we have interactions between the W, between all the gauge bosons, WZ and photon, and the Faraday-Popov ghosts. And the interaction strengths can be calculated. So in this way, you can obtain the full Feynman rules for the standard model in this RxI gauge fixing, which is the gauge fixing typically used in practical calculations, especially at the loop level. Any questions to this topic? Because that is the end of this section on gauge fixing and BRST invariance. Afterwards, we will start with a new topic. Are you able to calculate in detail all the prefactors? So the information is in principle there, it is just a matter of time. Not much time, but a little bit of time to plug in all the prefactors, including -I from the generic BRST transformations, applying them to the standard model. And then you will get these interactions. And compared to QCD, the new thing is that the ghosts have a mass. The mass is correlated to the gauge boson masses, and they have interactions with the Higgs fields. Precisely with those Higgs fields which have vacuum expectation values and which are relevant for the spontaneous symmetry breaking and for the generation of the W and Z boson masses. We also, a few hours ago, discussed the masses of the would-be Goldstone bosons, right? They also come from the gauge fixing. So this very same gauge fixing term contains mass terms also for the Goldstone bosons. And they are also correlated to the W and Z boson masses. And it would be a simple calculation to show that the Goldstone boson masses and the ghost masses are identical. They are the same. And that is actually necessary in order to, for the final result for physical quantities to be independent of the gauge, because these masses generate poles in propagators and therefore particular analytical contributions to Feynman diagrams. And the poles from the ghost propagators and from the Goldstone boson propagators are at the same position, and therefore they have the chance of cancelling each other out, such that the final result is independent of these Xi-dependent masses. So this is a structural feature, and of course the equality of the Goldstone boson and ghost masses, all of them are unphysical, and the equality follows from the BRST invariance of the theory. Good. Now let me check something here. Then let us go to the next topic. Custodial symmetry, a very physical and important topic for phenomenology of the standard model, and in particular for current electroweak precision physics. Custodial symmetry is related to one of the miracles of the standard model that we have already observed. Namely, one such miracle was that in our notation, CW was equal to C theta. And let us remember what that means. CW for us is an abbreviation for the ratio of the W and Z boson masses. And on the other hand, the cosine of the weak mixing angle theta W was defined via the gauge couplings, namely tangent of theta was defined as the ratio GY divided by GW. And this equality is valid at tree level, and remember that we are working at tree level at the moment in the standard model. So this is an equality that comes out of the standard model calculations. We discussed it and we stressed that it is very important because experimentally this equality is approximately valid. It is approximately valid up to corrections of a few percent, which can in the standard model be attributed to loop corrections. But at tree level we have an exact equality here. And that is one of the miracles because it is not built into the definition of the standard model, but it comes out of it. And it follows from the particular field content in the scalar sector, in other words, in the Higgs sector. The fact that the electroweak symmetry is broken by a Higgs doublet instead of a Higgs triplet leads to this equation. But you have seen in the exercise that a Higgs triplet would give rise to a completely different mass ratio. And so let us also relate this to a different quantity. There is the parameter rho 3, the tree level rho parameter, which is exactly the ratio here, let's say mw divided by mz times cosine theta, and defined in this way, the rho 3 parameter in the standard model is apparently 1. Okay. So you can formulate the same miracle by saying the tree level rho parameter in the standard model is 1. And this whole section is
طبعا كما ذكرنا من قبل أن الدبليو لاجرانج في الدبليو أو في الكوفاريانت ديريفيتيف بالنسبة للترم للدبليو، وترم خاص بالمجال المغناطيسي اللي هو تغيرات المجال المغناطيسي بالنسبة للفضاء دون الزمن، والزد فيه تغيرات المجال المغناطيسي والكهربائي. واخترنا في الجيج interaction with matter with Higgs، اخترنا أن MZ كتلة الزي هي في المجال الكهربائي، في المجال الكهربائي معتمد على الزمن، وبالتالي جاءتنا نسبة بين كتلة الW إلى كتلة الهيجز هي عبارة عن كوساين ثيتا، هي عبارة عن كوساين ثيتا. وذكرنا أنه الكوساين عندما يكون زيرو والزاوية تكون زيرو فإن الطاقة تكون عالية، وبالتالي نجد أن الزي والدبليو يساوي 1، الاثنان يخرجان بطريقة واحدة، يعني يكونان لديهم خواص مغناطيسية صرفة. وإذا كانت زاوية 90 فإن واحد فيهم يكون لديه خواص كهربائية والثاني لا. الزي سيكون لديه خواص كهربائية، وبالتالي نجد أن الفرق بينهما هو الصفر. أنا ما أعتقد ذلك. كوساين زين بصفر، فالسؤال الذي يطرح نفسه: ما الذي يجعل الصفر تختفي وبالتالي يصبح أقصد الزي تختفي وبالتالي يصبح الدبليو على صفر، أقصد الدبليو تختفي وبالتالي تبقى الصفر على زي يساوي صفر، شيء من هذا. لكن هذه سيظهر في الكاستوديال سيمتري، سنكتشف ماذا يعني إذا تم تحريك الزاوية، ماذا يحدث. تعالوا نشوف.
Understanding and illuminating the reason behind this, we want to identify a secret symmetry of the standard model, namely the so-called custodial symmetry, which is the origin of that relationship And identifying the symmetry makes you able to understand what happens if you change the standard model to physics beyond the standard model, depending on the properties of these beyond the standard model changes. Such a custodial symmetry either remains valid or it is invalid, and therefore different ways to extend the standard model can either keep this relationship or completely ruin it. And that is important to understand. So that is what we want to do now. And let us begin with the consequence of the symmetry breaking pattern of the gauge invariance in the electroweak standard model, namely the consequences of SU2 left cross U1 hypercharge is broken to U1 for electric charge. Let us assume this symmetry breaking pattern, which is of course the definition of the electroweak symmetry breaking, and let us use only this information and nothing else to see what follows from it. So let's look at a generic scalar sector with fields phi I, or we call it small phi I, plus Vi, such that you already see that the scalar fields are some number of scalar fields and they all might have some vacuum expectation values at tree level. And we consider gauge invariance under the gauge group SU2 left cross U1 hypercharge. And we assume that the vacuum is invariant under U1 electric charge, where electric charge is defined as T3 from the left-handed gauge group plus hypercharge. So that means if you act with T3 from left-handed plus hypercharge, if you act on this onto the vacuum, you get 0. This is the assumption. And now let us draw consequences from just this assumption and using nothing else. The claim is that, okay, let's first say the question is what are the consequences of this? And let's define again the mass matrix M square AB, as we did in the generic discussion of generic gauge theories with spontaneous symmetry breaking. This was the mass matrix for the vector bosons in the theory, and they are in general defined like this: Vi dagger times anticommutator of GA TA, GB TB IJ Vj, where here we use as an abbreviation, let's say the generator T4 is identified with hypercharge, just to make it simpler, because we have 4 generators, T1, T2, T3 for SU2 and hypercharge, and let's just call that T4. And let's also say G1, 2, 3, the gauge couplings, they are all identified with GW for the SU2 gauge group, and G4 is identified with GY for the hypercharge gauge group. Then we can simply write the generic mass matrix in the identical form to what we discussed in the generic case for the standard model, or for any theory which has the gauge group SU2 left cross U1 hypercharge. And let us now in this notation evaluate the consequences of for the mass matrix. And there is a very simple claim which I want to write down such that you will see better what we are aiming for. The claim is that the mass matrix has a certain structure. No matter what the concrete theory is, if we have this starting point, then the mass matrix automatically has a particular block form, namely it consists of a 2 by 2 block here for the indices 1 and 2, and this 2 by 2 block is actually proportional to the unit matrix. So here we have identical entries and here we have zeros, and the two identical entries we can call, let's call them GW square times VW square, and here the same GW square times VW square. So this is proportional to the unit matrix. It is obviously also proportional to GW square because clearly in the 1, 2 sector all the generators are multiplied with GW. So clearly in this sector GW square will always appear, but the main point is here there are two zeros and here these two entries are equal, and so they can be written as GW square times some prefactor, and let's call the prefactor VW square. Then we have another block matrix. Here this block matrix is automatically 0 and this block matrix is also automatically 0. And then we have a fourth block matrix, and this fourth block matrix is not proportional to a unit matrix, but it is a complicated matrix with determinant 0, and it can be written like this. Here GW square times a new constant time, let's say VZ square. So clearly the 3 element again is multiplied with GW square, so let's factor that out, and then there is some proportionality constant which I call VZ square, and that doesn't have to be the same proportionality constant as here. But then we know the rest. If this is like that, then here we have minus GW GY times the same VZ square. So only the gauge couplings are replaced in this form, and here we have the same minus GW GY times VZ square, and here we have GY square times VZ square with a plus. And then you see that the determinant of this block matrix is automatically 0 because the two lines are proportional to each other, and the eigenvalues are on the one hand 0 and the other eigenvalue is the combination of those two quantities here. So if this is the matrix, then we can immediately draw some conclusions, namely the W mass square from this matrix would be equal to this GW square times the proportionality constant VW square, so that this unit matrix directly gives masses to the W plus minus bosons, and this block matrix gives mass to the photon, which is 0, and to the Z, and the Z mass square is the other eigenvalue from this matrix, and this is simply this combination GW square plus GY square times the proportionality constant VZ square. And then you can look at.
طيب قبل أن نستمر نجد أن ما زال الموضوع محافظا قليلا، يعني الماتريكس هذه تعتبر خواص الكهربائية وخواص المغناطيسية، لكنها كأنها قلبت الصفوف أصبحت أعمدة، أو الأعمدة أصبحت صفوف، لأنه المفترض الأجزاء المعتمدة على الزمن تكون هي الفوق، والأجزاء المعتمدة على المسافة صرفة تكون هي التحت. هنا مقلوبة المصفوف هذه مقلوبة بحيث أنه الأجزاء المعتمدة على الزمن هي التحت، والأجزاء المعتمدة على المسافة أو على المكان هي الفوق. ونجد أن الاعتماد على الزمن ليس كاملا، وهذا واضح لأنه الزد الترم للزد أو الحد للزد فيه مجال كهربائي ومجال مغناطيسي، وهنا ذكر أن المجال الكهربائي يساوي المجال المغناطيسي، أو الاعتماد على المجال الكهربائي، الاعتماد على الزمن بالنسبة للمجال الكهربائي يساوي الاعتماد على الزمن بالنسبة للمجال المغناطيسي، اللي هو قال إنه T4 يساوي أو TA يساوي الواي. من هنا ذكر ذلك، وبالتالي نجد أن هناك تنافس في الزد، لكن في الدبليو ليس فيه تنافس. طيب جاء هنا حسب كتلة الدبليو، كتلة الدبليو عبارة عن جي تربيع في في دبليو تربيع، ما في حاجة. لكن لما جاء عند الزي وجدنا أنه هناك اثنان من الجيز طبعا الجي هي الكوبلنج كونستانت، اثنان من الجي تتنافسان فيها اللي هي جي دبليو وجي واي، والغربي هنا بإشارة زائد، هنا بإشارة زائد. هذا بالنسبة للكتلة المضروبة طبعا في في، وكأن جي دبليو أصبحت اثنين، جي دبليو مع جي واي ومضروبة في الفي. هذه هي كتلة الزي. فكتلة الزي تنقسم لقسمين، مجال كهربائي ومجال مغناطيسي، وجاء كتلة الدبليو هي مجال مغناطيسي. طيب تعال نشوف ماذا تخبرنا هذه الآلية.
Row 3 parameter, row 3 defined again in this way, mw squared divided by mz squared times cosine theta squared. Did I forget a square? Sorry about this. Please add a square here everywhere. This is the same thing squared. So here if we plug in the squares, then in the ratio, indeed the gauge couplings appear exactly in the form which is the one given by the cosine of the weak mixing angle. So the gauge couplings and the weak mixing angle drop out, and the only thing that remains is the ratio between these proportionality constants Vw square and Vz square. So it can be anything. In general, the row 3 parameter could be any value between 0 and infinity. And you see that the symmetry breaking pattern SU2 cross U1 goes to U1 hypercharge. Does not guarantee that the row parameter is any particular value. In particular, it doesn't lead to row equal 1, but row could be anything. And there, in this way, you see that the result in the standard model where row is 1 is special and corresponds to one of those miracles. And so that is the claim, and let us now prove the claim. Let us prove that the mass matrix, if we have the symmetry breaking pattern, leads to this block form. Let's do it here. So how can we prove this? We prove it by literally using the definitions, and what we can start with is that Q, the electric charge acting on these vacuum expectation values that we have, is 0, which is equivalent that T3 plus hypercharge is 0, or in this new notation we can also say T3 acting on V is equal to minus T4 acting on V, where, as I said, T4 stands just as a different symbol for hypercharge. So T3 and T4 act in opposite ways onto the vacuum expectation value. Then look at the definition of the mass matrix squared. It is obtained by acting with the generators onto the vacuum. So what happens if you look at specifically mass matrix with index, some index A, let's say A, and then 3, and compare it to the mass matrix square with some index 4. If you compare the indices 3 and 4, then the thing with the index 3 is obtained by acting with T3 onto the vacuum. But you also have a factor GW, so if we factor out 1 over GW, then this is just obtained by T3 acting on the vacuum. And if we factor out here a factor 1 over 3y, then this is obtained by acting with T4 onto the vacuum. But there is this relationship, and therefore we see that mass matrix third row with this normalization is minus to the fourth row with that normalization. And that immediately explains the entire 2 by 2 block in the lower right corner. So we immediately obtain this 2 by 2 block, which is proportional to GW square minus GW GY minus GW GY and plus GY square times some proportionality constant. This completely immediately follows from that. Therefore, we have already established half of what we need. And of course, this relationship doesn't tell us anything about the proportionality constant, which is therefore some unknown number, but it tells us about the structure of the prefactors in front of what we called VZ. Okay, so this is the first result. How can we prove the rest of the structure? The rest of the structure can be proved in this way. Let us start using the following. 0 is equal to the following. Let's say VI decker, and then let's put down commutator of Q times TA TB Vij. And let's use here only AB equal 1, 2, 3. So for the fourth, it's always even easier than for the first three components where we have the non-trivial SU2 commutation relations. So let's just stick to AB equal 1, 2, 3, and then we also do not have to care about the gauge couplings because they are always equal to GW and can be factored out. So why is that 0? Because the vacuum is annihilated by Q. Therefore, for one term of the commutator, Q acts onto the left onto V dagger and gives 0. For the other part of the commutator, Q acts onto the right onto the vacuum and also gives 0. So therefore, this is clearly 0. But now let us evaluate the commutator.
طبعا المجال الكهربائي والمجال المغناطيسي يعطيني هذا الكميوتيتر، لكن المجال المغناطيسي في بعضه لا يعطينا هذا الكميوتيتر، يعطينا أنتي، يعطينا نون أبيليان، وهذا واضح. لماذا؟ لأنه المجال المغناطيسي كميوتيشن في حدين يؤثر الحد الثالث، اللي هو إذا عملنا كميوتيشن بين إكس وواي يؤثر في الزد مباشرة. لكن بالنسبة بين المجال الكهربائي والمجال المغناطيسي ليس هناك تأثيرا، وبالتالي الانتقال من المجال الكهربائي للمجال المغناطيسي يكون بهذه السهولة. لكن الانتقال في المجال المغناطيسي فيما بينه يكون بيأثر مباشرة على المجال الثالث. إذا أثرنا على المجال المغناطيسي A في اتجاه X واتجاه Y، فإنه يؤثر مباشرة على المجال المغناطيسي في اتجاه Z، وهذا ما يجعل الانتراكشنز بين الكواركات وبين المجالات المغناطيسية، ويجعل هناك كوميونيكيشنز بينهما، وهو ما يجعل الفضاء ثنائي الأبعاد يدافع عن نفسه.
Let us evaluate the commutator. Q is equal to T3 plus hypercharge. And here we only use T1, 2, 3. So therefore, the hypercharge immediately commutes with those matrices, and therefore in the commutator the hypercharge can be dropped. However, T3 cannot be dropped, and then we can evaluate the commutator in the following way. Like in quantum mechanics, commutator with a product gives the sum of the two commutators. So we have on the one hand commutator of T3 with TA times TB plus TA times the commutator of T3 with TB. Okay? So we simply evaluate the double commutator in this way. And then this is the
طبعا هذا صحيح وما قلته من قبل خاطئ. لماذا؟ لأننا اعتبرت مجال كهربائي كامل، لكن هو ليس مجال كهربائي كامل، هو كومبينيشن، وأنا أخطأت بذلك. هو كومبينيشن، يعني كيو هذا عبارة عن كومبينيشن، ليس مجال كهربائي بالكامل، عبارة عن كومبينيشن بين مجال كهربائي ومجال مغناطيسي، لأنه عبارة عن تي 3 زائد تي 4. تي 4 تخصص الزمن، وهي تعبر عن المجالات كهربائية معتمدة على الزمن، والتي 3 هي جذر المجال المغناطيسي. فإذا الكوميوتيشن بينهما لا يساوي زيرو، برغم أنه هناك مكتوب يساوي زيرو لكن ليس يساوي زيرو. لكن عندما نعمل كومبينيشن يحصل هذا يساوي زيرو. فالكيو عبارة عن كومبينيشن. هذا الخطأ أنا ارتكبته.
zero, and for concrete choices of A and B, this gives us relationships between the matrix elements. Let us look at one example. Let us look, for example, at A equal B equal 1. What tells us the equation if A and B are equal to 1? If A and B are equal to 1, then we get 0 is equal to the following, namely, what is it equal to? VI dagger times commutator of T3 with T1. What is it? Do we know it, or is it unknown? T3, T1. Yeah, what is left? T3, T1 gives I times T2. And that is known because this is the SU2 algebra. So we have here I times T2 times T1. And here T1 plus T1, and T3 with T1 is again I times T2. Ij, Vj. Okay. Zooming out, the I doesn't really matter because the whole thing is 0, and then what we have here is between V dagger and V, we have anti-commutator of T1 and T2. That is exactly the definition of the matrix element with index 1, 2. So what does it mean? It means that we have proven the matrix element 1, 2 is 0. That is exactly our claim. So we have established this 0 here. What happens if you put here, for example, A equal 1 and B equal 2? 1, 2. What happens then? Just do it in your mind. A is 1 and B is 2. If A is 1 and B is 2, then we have here the same I T2 times T2, T2 square. And here we have T1, and here we have the commutator of T3 with T2 gives minus I times T1. So we will get here T2 square minus T1 square. T2 square minus T1 square is 0. That means we would get A equal 1, B equal 2, leads us to M square 1, 1 is equal to M square 2, 2. The two matrix elements are equal, which is exactly what I claimed here. And so on. I don't have to tell you what you have to do next in order to prove all the other zeros. If you do anything else, you will prove step by step that all the other matrix elements are 0. So similarly, you can completely establish the block structure. Okay. So and the main point was using the commutation relations between the electric charge and all the other generators, and the fact that the vacuum is annihilated by the electric charge. So that alone suffices to prove this structure. And so looking again at the result, we get one mass term for W plus minus. We have two charged gauge bosons, W plus and W minus, and they have the same mass, and that is compatible with U1 gauge invariance. So the W is charged under U1, and so we have two particle-antiparticle degrees of freedom with equal mass. That corresponds to that 2 by 2 unit matrix, and on the other hand, we have a massless gauge boson corresponding to the unbroken electric charge gauge group. So that is also a must. And we have a fourth massive gauge boson, the Z, and its mass is here unrelated to all the other masses. That is what we get from the symmetry breaking pattern. So if there is such a special result, rho equal to 1, which doesn't follow from the symmetry, we should identify some other mechanism which is responsible for this striking result, which also happens to agree with experiment. And apparently the gauge invariance is not the cause of this, so it must be something else. And people have searched for the symmetry which is responsible for rho equal to 1. And the outcome is this custodial symmetry, which I want to explain now. But let me first check the camera. Let me immediately show you the final result of the analysis, namely the discovery of the true symmetry pattern, which can explain rho equal to 1 at tree level. And let me illustrate it and discuss it outside of the standard model by only looking at symmetry patterns. And then afterwards, after explaining the symmetry pattern, I will show you why and how the standard model actually has the symmetry that I am now going to explain. But let's first explain the symmetry. Let us remember that so far we have looked at local gauge invariance of the standard model, but there is also global gauge invariance. And of course, global gauge invariance is like a corollary of local gauge invariance. If the standard model and the theory is invariant under local SU2 cross U1 gauge transformations, of course it is also invariant under global SU2 cross U1 gauge transformations. Global means X independent. However, it can be that there is a global symmetry which is a bigger symmetry than the one which is the local symmetry. And let us consider this particular case as a possibility such that there is a bigger global symmetry group than local gauge invariance. And then the picture is like this. Let me draw it.
طبعا global symmetry يقصد به المجال الكهربائي، حيث أنه يكون منتشر في جميع الاتجاهات، أو مثلا ليس هناك كسر في التناظر بين المجال الكهربائي والمجال المغناطيسي. هذا ما يسمى بالجلوبال invariance أو global symmetry. اللوكال سيمتري أيضا يعبر عن ذلك، لكن اللوكال سيمتري يمكن أن يكون يحمل في طياته hidden broken symmetry اللي هو كما ظهرت في نظرية ولم تظهر في هذه النظرية في الستاندرد موديل، بحيث أنه هناك انتقال من المجال الكهربائي للمجال المغناطيسي. هذا بفضل اللوكال انفارينس، لكنه في الحقيقة هو ليس انفارينس وإنما حصل له بروكن بواسطة الكتلة. الجلوبال يكون في المجال الكهربائي ويكون في الالكترومagnetic اللي هو في اليو 1. الجلوبال هو في اليو 1، واللوكال يكون موزع بين اليو 1 والSU2. والاس 2 يعبر عن مجال مغناطيسي والجيو 1 يعبر عن مجال كهربائي. فتعال نختبر هذا الأمر.
Big picture. So this corresponds to the symmetry group of our theory. Let's call it capital G. G would be the symmetry group under which the theory is invariant if you look only at global transformations. And then a subgroup of that, in general, a non-trivial subgroup might be the one which corresponds to local gauge invariance, and let's call that H. So that is just a subgroup in general. So that corresponds to local gauge invariance. And then there can be spontaneous symmetry breaking. So in the standard model, that would be SU2 cross U1. Then there is spontaneous symmetry breaking, and the spontaneous symmetry breaking can, of course, affect the full global symmetry group. And so there is a subgroup of that which is unbroken and a part of it which is broken. So what we can draw is the subgroup which corresponds to the spontaneously unbroken part. So let us call that curly G. So this is a curly G, corresponds to the unbroken by spontaneous symmetry breaking. And then there is, of course, some overlap, so some unbroken local gauge invariance, curly H. So that is basically the curly G. So this is a curly G, corresponds to the unbroken by spontaneous symmetry breaking. And then there is, of course, some overlap, so some unbroken local gauge invariance, curly H. And so that is basically the intersection of the group which is locally gauge invariant and the unbroken by spontaneous symmetry breaking. So in the standard model, we only know that this group, normal H, is SU2 cross U1, and the unbroken subgroup is U1 corresponding to electric charge. And now let us consider that there is actually behind it all a bigger symmetry group which contains that just as a subgroup. And let us assume the following structure. And in order to write down the structure, we actually neglect the hypercharge gauge coupling Gy. So let us set for the following discussion the hypercharge gauge coupling Gy to 0. And then we assume that the group capital G, the full global symmetry group, is bigger, namely it is the group SU2 left cross SU2 right. So it is a group with 6 generators instead of 4, a 6-dimensional Lie group instead of a 4-dimensional Lie group. So this H is, of course, SU2L cross U1 hypercharge, so that U1 hypercharge in this context would be like a subgroup of this SU2 right. And let us assume that the unbroken global group curly G, which is unbroken, is not only U1, but is actually SU2 custodial, which is the diagonal subgroup of the SU2 left cross SU2 right. So here, there is the word custodial appearing for the first time. This is the custodial group, and its generators are, I say, the diagonal subgroup. What that means in terms of generators is that we have TL corresponding to the left-handed SU2 plus TAR corresponding to the right-handed SU2. So these are three generators. This SU2 left and the SU2 right, they are independent SU2 groups. So that means that the right-handed and the left-handed generators, they completely commute between these two groups, left-right. But the sum of the two is again an object which satisfies the original SU2 commutation relations. Therefore, this sum generates a new SU2 group, which is the diagonal subgroup of SU2 left cross SU2 right. This will become probably also a little bit more clear by looking at the examples, but this is the completely general definition. And in the standard model, the local group curly H, it is electric charge that would correspond to just a one-dimensional U1 Lie group with one generator, and that would correspond to just T3 left plus T3 right. But we now assume that there is a bigger symmetry. Even in the vacuum, we have a three-dimensional Lie group which leaves the vacuum invariant. And that is the so-called custodial symmetry. So it is a global symmetry of the vacuum of the theory.
طبعا هناك شيء مخفي في هذه الفقرة. الجلوبال اللي هو البيج جروب اللي هي جي كابيتال لديها 6 degrees of freedom، وهذا 6 degrees of freedom معروفة جدا لأنه أولا هي تعتمد على المجال المغناطيسي فقط، لأنه نحن اعتبرنا أنه الجي واي يساوي 0، بالتالي المجال الكهربائي تم إلغاؤه، وهي تعتمد على المجال المغناطيسي فقط، وهي 6 degrees of freedom. وهذا واضح بأنه التفاضل بالنسبة للبي المجال المغناطيسي بالنسبة للزمن وبالنسبة للمكان فهي 6. وهي بعد ذلك تعتمد على اثنين، أولا لديها اثنين سب جروب اللي هو الاتش والكيرلي جي والهيجز. الغريب أنه كلهم في القطاع المسيطر عليه المجال المغناطيسي ما عدا الاتش. الاتش لديه U1 كلها U2 SU2 إلا الاتش لديه U1. يعني الاتش ما زال لديه U1، أو المفترض لا يكون لديه U1 نهائي، يكون كله في الاتش في SU2. ونجد أن ال والR منفصلان من بعض، اللي هو الليفت والرايت منفصلان من بعض، لأن المجالات المغناطيسية تكون شبيهة قريبة من الحرية الكاملة، لكن ليست حرية كاملة كما ذكرناه قبل قليل، لأن الانتي كوميوتيشن أو النون ابيليان، بحيث أنه إذا أثرت عملت كوميوتيشن بين مجالين اثنين ويصل حتما في المجال الثالث، فهي ليست حرية. طبعا هذه الكوميوتيشن يجب أن يكون درجات، يعني في نظريتي تقول أن الكوميوتيشن درجات، التأثير في الثالث درجات. لماذا؟ لأننا نحن ننتقل من فضاء ثنائي الأبعاد متحكم فيه وغير متناظر نهائيا، فضاء ثنائي الأبعاد غير متناظر نهائيا ومكسور فيه التناظر، إلى فضاء ثلاثي الأبعاد متناظر جزئيا بسبب الكتلة، ثم بعد ذلك يعني أو نقول رباعي الأبعاد متناظر جزئيا، ومع تضخم الكتلة يصبح متناظر كليا. مع تضخم الكتلة يصبح متناظر كليا. ربما عندما يصبح متناظر كليا ربما يكون الكوميوتيشن بين البعدين لا يؤثر في البعد الثالث، ربما يكون هذا، لكن الآن نحن نتكلم عن متناظر جزئيا ليس كليا. وهذا يعني أن التأثير لو عملت كوميوتيشن بين البعدين يؤثر في البعد الثالث مباشرة في مجال المكاني في الأبعاد المكانية. أما الأبعاد المكانية والزمنية لا يتأثر، يعني ما في كوميوتيشن بين التايم والإكس ولا التايم والواي إلا في حالة واحدة، إذا أثرت ذلك أو جعلت الكتلة ما ثابتة. إذا جعلت الكتلة ما ثابتة لأن هناك يكون هناك تأثير بين بين الزمن والمكان من ناحية الكوميوتيشن. فالمجال الكهربائي يعبر عن التغيرات الزمانية، والمجال المغناطيسي يعبر عن التغيرات المكانية. وبالتالي نجد أن بالمناسبة المجال الكهربائي لا يعبر عن التغيرات المكانية فقط، لأنه فيه جزء خاص بالمكان بالمناسبة، لا يعبر عن التغيرات الزمانية فقط. التغيرات الزمانية هي T00، يعني أول إيلمنت في المصفوفة، أول إيلمنت هو عبارة عن زماني بحت. الصف الأول كله والعمود الأول كله عبارة عن علاقة الزمان بالمكان، وهذا هو المجال الكهربائي، ويعطينا الشكل الدايفرجنت الذي يجعله منتشر في الأبعاد الثلاثة. المجال المغناطيسي لا يوجد له دايفرجنت، لكن هو عبارة عن دوائر، ولهذا هو يتعلق ب الإيلمنتس الداخلية للمصفوفة مع عدد زيرو، يعني جميع الإيلمنت ما عدا التي يحتويها أحد من الاندكسس هي زيرو. هذا هو المجال المغناطيسي. لهذا نجد أن المجال المغناطيسي يعتمد كليا على المكان. المجال الكهربائي يعتمد على الزمان ويعتمد على المكان، وربما هذا هو السبب الذي جعل H فيه U1 ولا تموت كليا. فالمجال الكهربائي لديه هذا الانتشار، المجال الكهربائي لديه اعتماد على الزمن واعتماد على المكان، أما المجال المغناطيسي هو اعتماد على المكان خالص. فنجد هنا أن Custodial Symmetry عبارة عن TL زائد TR في تحت الاندكسس A، والA يساوي 1 2 3 4 ما في طبعا، وتحتوي على تغيرات بالنسبة للمجال المغناطيسي في المكان. أعتقد أن التغيرات في مجال المغناطيسي بالنسبة للزمان، طبعا المغناطيس لديه أيضا زمان ومكان بالمناسبة، لأنه عبارة عن مشتقة في الزمان والمكان، وهذا شيء غريب جدا يعني في المعادلة أو في نظريتي. المجال الكهربائي أنا ما أعرف، لكن ربما يكون العكس، ربما يكون الاعتمادات الزمانية والمكانية يكون المجال المغناطيسي والاعتماد المكاني فقط للمجال الكهربائي، لكن لا أظن هذا صحيحا، لا أظن ذلك صحيحا. ربما أبحث في هذا الموضوع، ربما أكون مخطئ أن الاعتمادات الزمانية والمكانية تكون للمجال المغناطيسي، والاعتمادات المكانية فقط تكون للمجال الكهربائي، لأنه المجال الكهربائي يساوي مشتقة المجال المغناطيسي، ونحن جعلنا المجال الكهربائي المجال الكهربائي يساوي مشتقة المجال المغناطيسي للزمان، ونحن جعلنا المجال الكهربائي مشتقة بالنسبة للمكان. بالتالي غيرنا المصفوفة بحيث أن جعلنا المجال المغناطيسي مشتقة في المكان والزمان، وجعلنا المجال الكهربائي مشتقة في المكان فقط. إذا حصل ذلك، إذا كان هذا صحيح حسب كتاب الحلقة 54 و 55 وأيضا 56، إذا كان هذا الكلام صحيح فإن ما قلته كله في المحاضرات السابقة فقط أقلبوه. لكن أنا أعرف أنه T4 يعتبر خاصية زمانية بحتة، T4 هي خاصية زمانية بحتة، لأنها هي متعلقة بالزمان، ويساوي الزيرو، وبالتالي هناك اعتمادات على الزمان تم اختصارها. أبحث في هذا الأمر.
Okay, let us assume this structure and let us now go back to the mass matrix and calculate what is now the consequence of this assumed symmetry structure on the same mass matrix.
بالمناسبة الشحنة تعتمد على الزمان برضو، الشحنة بتعتمد على الزمان. إذا جعلتها زيرو هذه أنا اختصرت الاعتماد على الزمان. لا أعتقد أنه المجال المغناطيسي يعتمد على الزمان أيضا، ويعتمد على المكان، وبالتالي يمكن تعديل معادلتي بالمناسبة حلقة 54 55. يمكن تعديل المعادلة بدل أن نجعلها مجال مغناطيسي دالة في المكان والزمان، يمكن أن نجعلها دالة في المكان والمكان باختلاف الأمكنة. يمكن نفعل ذلك، ليست هناك مشكلة. راجعوا فقط الاشتقاقات والاستدلال الرياضي وحاولوا غيروا وشوفوا النتائج.
So what is the consequence for the mass matrix M square AB? And let's only look at A and B equal to 1, 2, 3. Since for the discussion we neglect the hypercharge gauge coupling, therefore clearly the fourth row and fourth column in this approximation would be 0. So the only non-trivial thing that we need to look at is this 3-3 matrix element, which so far was unrelated to the other two matrix elements, and now there will be a relationship. So let's derive this relationship. So now we have 0 is equal, so let's say 0 is equal to TA left plus TA right acting on the vacuum. So the vacuum is left invariant under all these generators for all A, right? Because that was our assumption. On the other hand, the mass matrix is composed only of the left-handed generators because they are the ones corresponding to the gauge group and the ones corresponding to the gauge boson masses. So the M square AB is just given as always V dagger I times, in this case GW square, times anti-commutator T left A with T left B acting on Vj. So T left because T left corresponds to the actual gauge interactions and to the gauge boson masses. So we see here this difference. The vacuum is left invariant under some combination of left and right-handed generators. The mass matrix is composed only of the left-handed generators. Now we can use the first equation in the second, and then we can again get 0 is equal to something similar to what we did before, Bi dagger, and then let's look at the commutator, TA left plus TRA commutator with, let's say, T left A, T left B, T left C, Ij, Vj. So that is 0 because this combination of generators leaves the vacuum invariant, and here I write the two generators which we need to construct the mass matrix. So now in this construction, TR has nothing to do with TL. TR completely commutes with TL. Therefore, in this commutation relation, it can be dropped. So this can be dropped because it anyway commutes with the left-handed generators, and then what remains is this TLA, comma TBL, TCL acting on Vj. And then we can go on just as we did before only that our mass matrix previously was only invariant if we have here the electric charge Q. So we got one condition from that. And now we have three conditions because the mass matrix is invariant under whatever generator we put here, T1, T2, T3. So that means the 3x3 part of the mass matrix is completely invariant under the full SU2 left. That is what this means. So the 3x3 part of M square AB is fully SU2 left invariant. And if a 3x3 matrix is fully invariant under this, then it means it must be proportional to the unit matrix. So in particular, that means M square 1, 1 is equal to M square 2, 2, and that is also equal to M square 3, 3. And this last equation is new. So we get from this that this block here, this 3x3 block, must be a unit matrix because it is invariant under the full SU2 left transformations. And that in this notation means the VW and VZ are equal proportionality constants. So let's write down the consequence for the mass matrix in a nice form. M square AB, now including the hypercharge, has the following structure. The same as this, only that VW is equal to VZ. So we have here GW square, VW square, GW square, VW square, GW square, VW square, all the same. And then here we have the other block, which we already know from just U1 invariance, minus GW, GY, VW square, and here the same, minus GW, GY, and here plus GY square, VW square. And so to highlight it, this equality of the three entries, this is new and corresponds to custodial symmetry. So we have a full SU2 invariance of the first 3x3 block of the mass matrix. And on the other hand, the fact that we have here the yellow 2x2 block followed just from U1 invariance of the vacuum. And if we combine both pieces of information, then we have here a correlation, namely this block gives us the Z mass, and the Z mass is now proportional to the same VW as the W boson mass. So therefore, in this context where we have this custodial symmetry of the vacuum, we get rho 3 automatically at tree level is equal to 1. So this is this new custodial symmetry, which corresponds to this bigger symmetry pattern. So any questions to the derivation? Yep. Yes, so for any A, this is, so you have the same A here and here, but then you can choose any A and you have 3 different generators and all of them leave the vacuum invariant. That is the point. So each of those combinations leaves the vacuum invariant. And there are 3 of them, and all of them can be used here. And then this is this tricky thing. The vacuum stays invariant if you look at the combination left-right. But if you go to the consequence for the mass matrix, the right-handed part drops out entirely. And what simply is important now is that the vacuum and the mass matrix is invariant under this left-handed SU2. And the left-handed SU2 means that you have now this 3x3 matrix, which is invariant under any SU2 transformation, and therefore it must be the unit matrix up to a factor. Or I mean, you can do all the calculations in detail. You don't have to say it in words. It leaves the matrix invariant. Plug in all possible combinations of indices, and then you will see that after a while these matrix elements must be equal in a way similar to what we did before. So if you plug in here T1, A equal 1, and here 2, 3, then you will get a relationship that the matrix element 2, 2 will be equal to the matrix element 3, 3, which gives you the desired relationship. And again, you can compare this to the previous case. In the previous case, we basically had, instead of this, we had the electric charge Q, which was T3 plus Y. And then again, Y would drop out of the equation because it commutes with everything, just like TR. But here remains only T3. And from the T3, we get only a subset of the relationships. And now we have T1, T2, and T3. And therefore, we get the more powerful consequence. And of course, you might, at the moment, you might not have an intuition for what the TR actually is, because that has now been completely newly invented, and what it means in the standard model will come next. But the point is, and maybe that is a historical remark, the entire discussion came up not immediately in the standard model, but in ways to extend the standard model, where it was observed that some extensions destroy the row parameter equality and other extensions do not destroy the row parameter equality, and then people started to investigate what is the cause of this and how can we construct extensions of the standard model which automatically in a guaranteed way lead to row equal 1, and in this way one observed and understood this particular symmetry breaking pattern. And so this was in particular first observed in the context of so-called technicolor models. For electroweak symmetry breaking, where you assume that the Higgs sector is not an elementary scalar field, but a much more complicated Higgs sector which comes from non-perturbative effects. And then if these non-perturbative effects follow such a symmetry pattern, then automatically, no matter whether you understand the details of non-perturbative dynamics or not, you know that they lead to row equal 1, which was very important to know. Okay, yeah. I wouldn't say only, but what do you mean by only? Well, no. So I don't know what you have in mind exactly, but if you, in the standard model, we will now make this explicit, because in the standard model this pattern is realized, and I will show you how and why. And then you understand it, hopefully, and since you understand it, in the future afterwards we can discuss, go back to the ordinary discussions of the standard model, and you can keep this in the back of your mind, if that answers your question. But on the other hand, if you want to extend the standard model and study physics beyond it, like Technicolor, supersymmetry, or some other extensions of the standard model, like Higgs triplet, Higgs singlet extensions, then you should also keep in mind this symmetry breaking structure, and you should at least know whether your favorite extension has such a symmetry or not. You are not obliged to only consider extensions which have this custodial symmetry. It is fair enough to consider extensions which do not have this symmetry breaking, but then you should know very acutely that your rho can be anything, and you should make sure in another way that it doesn't violate experimental results.
أنا عندي معلومة عايز أضيفها خطرت لي الآن في خصوص الكاستوديال سيمتري. اللي رأينا أن مصفوفة هي مصفوفة ترانسبوزيت، يعني جاي من كلمة ترانسبوز، هي مغلوبة. هذه المصفوفة مغلوبة بحيث المجال المغناطيسي مفترض يكون تحت، المجال الكهربائي يكون فوق، وكما أن الزمن يكون فوق والمكان يكون تحت. لكن في حالات يمكن أن تغلب هذه المصفوفة. حالات ماذا؟ تعالوا أوريكم الحالات. إذا كان الأمر صحيحا فهذا اختراق كبير جدا لنظريتي، لهذا سأجتهد في أن أشرح لكم. طيب الحالات هي عند التفاعلات القوية جدا والمسافات الصغيرة، فإن الحد الثاني هذا يكون مسيطرا وبعلامته السالب هذه، والدي آر على الدي تي ستكون سالب، دي آر على سي دي تي تكون سالب 2 جي ام على سي تربيع آر. طيب ماذا يدل على هذا الموضوع؟ يدل هنا، تعالوا هنا، إشارة السالب تعطينا أن في هذا المترية أن الزمان يصبح مكان والمكان يصبح زمان. بالتالي مشتقة المجال المغناطيسي في كتاب الحلقة 54 هو مشتقة من المكان والزمان، فيصبح مشتقة للمكان والمكان. جميل. والمجال الكهربائي الذي هو دالة في الزمان سيكون دالة في هو دالة في الزمان، سيكون في أيضا دالة في الزمان. لكن الخلاف يأتي وين؟ الخلاف إنه أحد أبعاد المكان يصبح زمانا. طبعا هذه المعادلة في المحاور القطبية، إذن المحاور القطبية لا تعطينا المعلومة دقيقة لأن في زاوية سيتا وفاي، نحن لا نريد ذلك، نحن نريد دالة في إكس وواي زد، فيعتبر هذه المحاور كارتيزية. فبدلنا بين الزمن، محور الزمن، ما أي واحد من المحاور سواء كان إكس وواي ولا زد، فبالتالي نجعل مجال الكهربائي أيضا دالة في الزمان ما مشكلة، لكن مجال المغناطيسي يتحول دالة في المكان. تترجم في هذه المصفوفة بالترانسبوز. طيب أين الإشكالية؟ هنا الإشكالية إنه إذا استطعنا أن نحول، هذا فرع من الموضوع، إذا استطعنا أن نحول المكان لزمان، المكان أو الزمان لمكان، ما الذي يمنع أن يكون الزمان لديه 3 أبعاد؟ يعني مثلا نحن نتحدث عن تحويل إكس وواي وزد إلى زمان، بالتالي كلها ستأخذ إشارة سالب، والتي سيأخذ إشارة موجب، لأنه سيصبح مكان مثلا، أو العكس صحيح. فبالتالي نجد أن الدالة ستكون في 3 أبعاد للزمان مقابل بعد واحد للمكان. تخيل هذا يكون موجود داخل تفاعل كيميائي، تفاعل دون ذري، الأبعاد تنقلب مكان ومكان تنقلب زمان وزمان ينقلب مكان. هذا ما يحدث داخل الثقب الأسود طبعا، لكن لاحظ تخيل أنه حصل هنا في تفاعل كيميائي، تفاعل دون ذري، ماذا يحدث؟ يصبح الزمان لديه 3 أبعاد والمكان لديه بعد واحد، وحسب هذه المعادلة لا فرق بين الزمان والمكان في أنه هذه الأبعاد تتقارب بسبب الكتلة فقط، وأن سرعة الضوء مضروبة دائما في الزمان، وبالتالي هناك ستكون مضروبة في المكان، وستكون هناك التقارب في الأبعاد بسبب الكتلة. لكن تخيل أن كتلة الحجم فيها دالة في الزمان وليس في المكان، ولأن الزمان لديه 3 أبعاد، والكمية الكتلة فيها في هذا الحجم، كمية الكتلة وكثافة الكتلية هي عبارة عن دالة في الزمان والمكان كما تعطيها هذه المعادلة. فتخيل كيف نرى هذا الفضاء ونحن في واقعنا هذا. يعني نحن نريد أن نكتشف بالديتكتورز ونكتشف بمثلا 4 dimensional microscope هذا الواقع الجديد، الزمان ينقلب مكان ومكان ينقلب الزمان. كيف يكون هذا الكشف؟ هذا ما ينتج من الكاستوديال سيمتري. فابحث بهذه المخيلة، ابحث في هذا النوع من السيمتري، ربما تكتشف أشياء خطيرة ومهمة جدا جدا، مثل السوبر كوندكتيفيتي. بالمناسبة السوبر كوندكتيفيتي لها نفس التأثير، حيث أنه داخل الكتلة تقترب، ممكن تطبيق هذه المعادلة طبعا. داخل الكتلة عند درجة حرارة قريبة من الصفر فإن الكتلة تتضخم والخواص المغناطيسية تزيد بالمناسبة، وبالتالي تعطينا معادلة شبيهة بهذا. وربما يكون داخل هذه القطعة السيراميك ولا داخل المادة التي فيها التوصيل الفائق ربما تصل مرحلة بحيث أنه تنقلب الأبعاد. ماذا يحدث في مادة انقلبت فيها الأبعاد؟ وماذا يحدث للمجال المغناطيسي القوي جدا في هذه المادة؟ فهذه أرض خصبة للبحث.
Okay, let us now look at the standard model. And for this, let us consider the case where the hypercharge gauge coupling is actually 0, and where in the Yukawa sector the up quark Yukawa coupling is equal to the down quark Yukawa coupling, and we ignore the leptons. Which is of course not really possible because of the gauge anomalies that we discussed the last time, but anyway, let us ignore them, or otherwise set the Yukawa coupling of the leptons to 0. Such that they do not interact with the Higgs. In this approximation, which is really an approximation to the standard model, the standard model develops this additional custodial symmetry, and before electroweak symmetry breaking, it develops this bigger global symmetry group corresponding to SU2 left cross SU2R. And you see from this that ultimately the symmetry is actually broken, not spontaneously broken, but it is broken by the fact that the hypercharge gauge coupling is non-zero, and by the fact that the up and down Yukawa couplings are not equal. So these things break the custodial symmetry explicitly, and we will discuss at the end what that means. But let's first do this approximation, which is a numerical approximation to the standard model, and then discuss this symmetry. So let us write capital QL for the left-handed quarks as we always did, UL DL for the left-handed doublet. But let us also write a right-handed quark doublet UR DR, which we have not done before because the UR and DR, they are individually singlets under SU2, right? But let us now write them as a doublet called QR, a right-handed doublet. And let us also write the Higgs fields as this, this sort of curly H. Let us write the Higgs field in this way. How do we write it? Phi tilde, comma, phi, where phi tilde is this SU2 transformation with the epsilon tensor. So phi tilde I is equal to epsilon ij phi dagger j. So this is this object which we need in the top quark Yukawa coupling, if you remember, right? We needed this, we called it baryon-like SU2 combination where we connect two doublets with an epsilon tensor. And here we first introduce simply such an epsilon transformed doublet, which is just another doublet according to our discussion from before. So if this is an SU2 doublet, then this is also an SU2L doublet, given our discussion from before when we looked at the top quark Yukawa coupling. So what that means is that we now write next to each other the two doublets, so we get a 2 by 2 matrix, and the matrix entries are on the right. First of all, the matrix entries for the actual normal Higgs doublet. So let's call it phi plus and phi 0. And here on the left column, we have the following, namely because of the epsilon tensor, we have here phi 0 dagger, and here minus phi plus dagger. So we write the Higgs field in this matrix form. Then let's look at some connections. What happens if you do H dagger H in terms of this matrix and take the trace? If you take the trace of this, then first H dagger H gives you row times column. So H dagger H contains on the one hand the column and the row phi dagger times phi, the whole doublet dagger times itself. And it also contains phi tilde dagger times phi tilde. But phi tilde dagger times phi tilde is the same as the original phi, and so from here we get the sum of the diagonal elements. So this is just phi dagger times phi plus phi tilde dagger times phi tilde, but that is the same as 2 times phi dagger times phi. So this is an SU2 invariant combination. So this is something that we know which appears in our standard model Lagrangian, and in terms of the new curly H notation, we can write this as 1/2 of the trace of the matrix H dagger H. And so in this way, let's also remind ourselves of the Yukawa couplings. The Yukawa couplings contained the top quark Yukawa coupling times QL bar times phi tilde. This is exactly this phi tilde times QR plus YD times QL bar times the ordinary phi times dr plus the leptons, which we ignore. Okay, so this was our Lagrangian for the Yukawa couplings involving the phi tilde and the phi. And we discussed that this is gauge invariant because of the epsilon tensor. And now, having all this notation at hand, we can write the full standard model Lagrangian in a slightly different way, namely L standard model can now be written as follows. Namely, we have the kinetic terms for the left-handed quarks, I d slash times q left, so q left bar q left, and the covariant derivative in between. And then we have a covariant derivative for ur and for dr, but there is no problem in combining them in such a vector notation, qr bar times id slash times qr. So then we have summarized the two terms for the right-handed quark singlets just by using the new notation. Then there is the Higgs potential term, and the Higgs potential depends only on phi dagger phi. That can now be written in terms of the trace. So we have minus 1/2 mu square times trace of h dagger h. And we have the lambda term minus lambda over 4 times the same trace squared. So I think we had here lambda over 2 and here 1/2 in the square. That is our Higgs potential, written with a matrix valued Higgs field. And then we can also write our Yukawa Lagrangian. Our Yukawa Lagrangian now can be written in this way. If the Yukawa couplings are equal, then the two terms can be combined and they just look like this. Y. Let's say we call the common Yukawa coupling, we call just Y. Then we have here Y times QL bar times the matrix valued Higgs field H times the right-handed quark doublet QR. And then by evaluating it, you get exactly that the down type part, which is the lower component, gets multiplied with the original phi and QL, and the up type part gets multiplied with phi tilde and QL. So this summarizes both Yukawa interactions. And then we have also the kinetic terms for the gauge fields, which we do not have to rewrite. But here you see two things, or three. First of all, you can combine the right-handed quarks to something like a right-handed doublet. This doesn't transform under gauge transformations in a doublet sort of way, but nevertheless we can write it like a doublet. The Higgs can be written as a 2x2 matrix, and the Yukawa couplings can be neatly compactified to one expression if the Yukawa couplings happen to be equal. And then it connects a left-handed doublet, a right-handed doublet, and a Higgs mass matrix. And the Higgs potential also can be written such that it only depends on this matrix. And now the additional symmetry of the standard model becomes manifest. Namely, what is now the global symmetry, in other words, non-gauged, non-local symmetry, is the following. Namely, we can transform QL, the left-handed quark doublet, with a UL 2x2 matrix. UL is element of SU2L. So this is an SU2 matrix. Then QR goes to UR times QR, where UR is another SU2 matrix. So it's an element of an independent SU2R group. So there are two completely different and completely independent 2x2 matrices, both SU2 kind of matrices. Then we transform this, and then we immediately see that this kinetic term is invariant under this 2x2 matrix because U dagger U drops out. This is also invariant even though that has nothing to do with gauge transformations, but because this UR matrix is global, X independent, the derivative doesn't do anything, and we simply get again UR dagger times UR drops out. So this kinetic term is also invariant. And then we can define the Higgs field matrix transforms like as follows, namely, how does it transform? From the left with UL and from the right with UR dagger. So it transforms from the left and from the right with two different matrices, and then you see what happens with the trace. H dagger H, in H dagger H you obtain immediately UL dagger times UL drops out, and then what remains here is UR and UR dagger on the left and right, but because of the trace UR and UR dagger also drop out. So this trace is invariant under this transformation, even if you have two completely independent SU2 matrices. So the second line is also invariant, because here and here the same trace appears. And now how about the Yukawa coupling? The Yukawa coupling is also invariant under this beautiful new transformation. So QL transforms here with UL dagger, and H transforms with UL, so UL drops out. Then we get here UR dagger times UR also drops out. So the Yukawa coupling is also invariant under this transformation here. So, and maybe let me add also the transformation of the gauge bosons. So that can be written in this way. TA times WA mu under global gauge transformations, that simply transforms in a similar way as the Higgs field matrix. So that is a 2 by 2 matrix, and that transforms from the left with UL and from the right with UL dagger. So TA WA mu. That is something that appears inside of the covariant derivative of the left-handed quark doublet. There appears exactly this combination, and this combination behaves like this, where UL is an X-independent SU2 matrix. So under global gauge transformations, the gauge bosons simply transform in a linear way like matter fields. Okay, and then, as I said, the Lagrangian is invariant. And this symmetry has two independent SU2 transformations, and therefore the symmetry group is SU2 left times SU2 right. So we see that our theory, the standard model before a symmetry breaking, has exactly this global symmetry group SU2 left cross SU2 right, as it was assumed for this custodial symmetry structure. So that is now made manifest. And again, it was made manifest by combining the right-handed singlets into a right-handed doublet, a very natural thing to do, and then transforming the doublet under such a right-handed SU2. And for the Higgs field, we do this matrix transformation. Now, how about the vacuum? How about the battery? Okay. So how about the vacuum? So in this matrix form, the Higgs in the vacuum has the following structure, namely the phi tilde. So the neutral components become V over square root of 2. So this matrix becomes this one. And what do you see? This matrix is proportional to the unit matrix times a proportionality constant V over square root of 2. And this matrix under this SU2 cross SU2 transforms with UL from the left and UR dagger from the right. So you see that it is invariant under special SU2 cross SU2 transformations, namely if the two are equal. if UL is equal to U right. So if the two matrices are equal, and then H vacuum goes into UL times H vacuum times UL dagger, the same. And since this is proportional to the unit matrix, the two matrices drop out, and that is equal to the vacuum itself. So the vacuum is invariant under a full SU2 symmetry group. Namely, you have here a full SU2 at your disposal. But the SU2 transformations that you need to choose are the diagonal subgroup of the original SU2 left cross SU2 right in this sense. So in words, this corresponds to the diagonal subgroup. And the name would be SU2 custodial. SU2C is equal to the SU2 left equal to right, let's say. And the corresponding generators are TA left plus TA right. And that is exactly the symmetry structure that we had to assume. So this is in line with the general discussion. Okay, so let us just end the discussion by saying something about violations of this custodial symmetry. In the standard model, there are violations of custodial symmetry. Namely, in the vacuum, we have the symmetry under the assumption that the hypercharge coupling is neglected and under the assumption that the Yukawa couplings for up and down sectors are equal. And of course, they are not equal. So in the standard model, Gy is actually non-zero and the hypercharges, the Yukawa couplings of up and down are non-zero. And so this is a violation of the custodial symmetry. In particular, for the Yukawa couplings, you see immediately that there is no way that you can write down this term in this simple form. And actually, if you look at 3 generations, then you have the top quark compared to the bottom quark. And here the Yukawa couplings are not only completely different, but also numerically very sizable. So this difference between top and bottom Yukawa couplings is a very, very strong breaking of custodial symmetry. And that is a weaker.
من هنا نستطيع أن نعرف أنه الكاستوديال سيمتري يخبرنا عن الاختلافات في الكتل. إذا الكاستوديال سيمتري تعطينا ماذا؟ تعطينا كتاب تخبرنا عن كتاب الحالة 554 وهو كسر التيار نيزر، حيث أنه يكون المشتقة بالنسبة للتيار نيزر لا يساوي 0، وهذا يعطينا اختلاف في الكتل. ما دام ذكر المحاضر أن الكاستوديال سيمتري عندما يكون اليوكاوا كوبلينج لا تتساوى وتكون الهايبر تشارج لا تساوي زيرو، فإن اليوكاوا للتوب يكون أكبر كثيرا من البطن، وهذا يعطينا اختلاف كبير في الكتل. وهذا يعني أن الأمر ناتج من ماذا؟ ناتج من اعتبار أن المجال الكهربائي الاعتمادات على الزمن المجال الكهربائي تعمل وليس الزيرو. وهذا واضح من نظريتي أو من المعادلة التي قابلتها قبل قليل، المشتقة بالنسبة للمكان على المشتقة بالنسبة للزمان تعطينا الكتلة والتغير في الكتلة، فبالتالي نستطيع أن نتتبع التغير في الكتلة من خلال المشتقة في المكان على المشتقة في الزمان، وهذا يعطينا الاختلاف في الكتل، يعطينا الاختلاف في الكتل، أنك تتتبع الزمان، تتتبع الكتلة من نشأتها من صغرها حتى كبرها، بالتالي تستطيع أن تقارب بين الكتل. فهذه الآلية لديها، فهذه الطريقة لديها آلية معينة بحيث أن تستطيع الكاستوديال سيمتري أن تخبرنا بالاختلاف في الكتل. فقط أن نجعل اليوكاوا لا يساوي اليوكاوا بين الدبليو بين الطب والبوتوم لا يتساوان، ولا نجعل لا تتساوى. والشيء الثاني نجعل الهايبر تشارج لا تساوي الزيرو، لأن الهايبر تشارج تعبر عن الاعتماد على الاشتقاقات الزمانية. إذا الاعتماد على الاشتقاقات الزمانية ولا الفرق بينه والاعتماد على الاشتقاقات المكانية تعطينا الفرق في الكتل، وهذا ما ذكرته نظريتي. هذا أمر جميل جدا.
Breaking. The point is, however, that if you calculate at tree level, then both effects do not matter, because you see that the general structure of this, even with neglected Yukawa coupling, is sufficient to guarantee this 3x3 part of the mass matrix, which we had here. So the three entries are equal. That follows from this discussion, and that consequence is not lost even for non-zero hypercharge. And at tree level, the Yukawa couplings do not play any role at all in the calculation of the gauge boson mass matrices. Therefore, both breakings do not disturb the tree level discussion. And that means these breakings can only enter via loop corrections at a higher order level. At higher orders. And for example, there is then delta rho at the one loop level from the top and bottom sector, which is the biggest effect, as you can understand from the symmetry discussion, and that is about 1% order of magnitude. And so then you can now understand how it can happen that at tree level you have exact equalities between all these different mixing angles, but via loops in particular from here you get percent level corrections, and those percent level corrections are then exactly the ones that you need in order to get really agreement between standard model theory and experiment. Because in experiment one observes percent level differences between all those different quantities that we defined. So that is very nice, and so if you do the calculations, then the results from this agree actually very well with experimental data. So that is one thing. So in the standard model you get violations at higher orders from both effects. So this also gives rise to loop corrections which are smaller than percent level.
بالمناسبة أنا جاتني أيضا فكرة نحن نجد أن الزي بوزون أكبر أعلى كتلة من الدبليو بوزون، وهذا لأنه الزي بوزون لديه اعتمادات على الزمان أو اعتمادات على المجال الكهربائي، والدبليو عبارة عن مجال مغناطيسي خالص. إذن المجال الكهربائي لا ينتهي بالكلية إلى تفاعلات الدبليو والزي، إلا في حالة إنه تفاعل يكون عميقا جدا، بالتالي يكون الاعتماد كله على المجال المغناطيسي. لكن إذا كان التفاعل ليس عميقا خالص فإن الاعتمادات على المجال الكهربائي لا يكون زيرو، وهذا ما يعطينا أن الزي أكبر من الدبليو. الدبليو 80 والزي عبارة عن 90، لأنه الزي يعطينا داخله تي 3 زائد الجي في تي 3 زائد الواي في جي واي، والواي تعتبر الهايبر تشارج التي تعبر عن الاعتمادات الزمانية اللي هي المجال الكهربائي، والتي 3 أو التي اي تعبر عن المجال المغناطيسي، بين أن الدبليو فقط نعبر به عن التي اي اللي هو الاي تاخذ 1 2 3. في حالة الزي التي لا تاخذ 1 2 3، انما تاخذ تي 3 او تي نعم تي 3 فقط. فنجد ان الزي تعتمد على المجال الكهربائي، ومجال الكهرباء لا ينتهي نهائيا، ولهذا اعطى التي اعطاها كتله اضافيه، اعطى الزي كتله اضافيه. لماذا؟ لان المجال الكهربائي لديه اعتمادات مكانيه وزمانيه ايضا، وهذا هو الفرق. المجال المغناطيسي لديه اعتمادات مكانيه فقط، المجال الكهربائي لديه اعتمادات زمانيه ومكانيه، مثل الاليمنت واحد، الاندكس في الاليمنت 1 0 1 اي. المجال المغناطيسي اي جي، هناك 0 اي، فهذا يعطينا كتلة إضافية للزي. هذه فكرة جاءتني الآن. إذا المجال الكهربائي لا ينتهي نهائي، ونجد أن الدبليو تعتبر تفاعل عميق جدا من الزي تفاعل ليس عميق جدا، أما الدبليو تفاعل عميق جدا، بالرغم أن التفاعل العميق يفترض يخرج كتل أعلى من التفاعل غير العميق، أو ربما الزي والدبليو تفاعلات عميقة، لكن في هذه الحالة الطاقة لم تصل الوضع المطلوب لهنا، لهذه الطاقة لم تصل الوضع المطلوب بحيث أنه تغلب الأبعاد كلها، أو تصل إلى 2 جي ام على سي تربيع ار، ربما يكون ذلك. يعني الطاقة عالية، طاقة التفاعل عالية، لكن لم تصل لهذا، وهذا يعني أننا إذا زدنا الطاقة أكثر فإن الزي سيكون مساويا تماما للجي، وهي الكوساين ثيتا التي موجودة بين النسبة بين الزي وكتلة الزي وكتلة الدبليو، أنه إذا زدنا الطاقة لدرجة بعيدة جدا فإن الكوساين ثيتا ستكون يساوي 0، فبالتالي كتلة الزي يساوي كتلة الجي، وبالتالي نكون انتهينا من المجالات المغناطيسية المعتمدة على المجالات الكهربائية المعتمدة على الزمن. هذا أيضا مدعاة للبحث.
And what happens now in physics beyond the standard model? In physics beyond the standard model, you also have, of course, gy unequal to 0, and you also have y top unequal to y bottom. That is, of course, clearly the case as well. But in addition, you might have additional particles which, like top and bottom, additionally break custodial symmetry. So you might have possibly additional terms in L which similar to top bottom, which break the custodial symmetry. And also breaking initially this SU2 left cross SU2R. So for example, in supersymmetry, you can easily understand that if you have superpartners to all the fields, then there are superpartners like stops and bottoms. They would similarly break the SU2 right, just like the ordinary top and bottom. And so then you have additional sources of custodial symmetry violation. And the second possibility is that you have new tree-level breakings of SU2C by row 3 not equal to 1. And that, for example, happens if we have a Higgs triplet.
طبعا الهيكس تريبلت يعني الهيكس 3 مرات، والهيكس 3 مرات يعني تفاعل عالي جدا، وبالتالي يؤدي إلى رو لا تساوي 1، يعني كوساين ثيتا لا تساوي 1، وهذا يعني طاقة عالية. فهذا أيضا اتفق مع نظريتي، ولديه عواقب أيضا ربما نراها وربما لا، لكن يمكن العلماء يبحثوا فيها.
As we discussed in the exercise, Higgs triplets give immediately rise to row 3 unequal to 1, and that is of course a direct breaking of this custodial symmetry, and it is phenomenologically important. So therefore you now understand what you need to make sure in extensions of the standard model, namely experiment agrees well with the standard model in this sector that we are talking about. Therefore the breaking of custodial symmetry in the standard model coming from these effects is non-zero, but exactly enough to basically guarantee agreement with experiment. So changes of the standard model should not ruin this structure. Therefore, row 3 unequal to 1 must be very small. So Higgs triplets, if they exist, must have a very small vacuum expectation value, which is a constraint on them. Models with many additional new fields and particles and new interactions must make sure that the additional breaking of custodial symmetry must not be too large in order to ruin agreement with experimental data. On the other hand, if there are experiments like the one recently where the W mass is now very much away from the standard model prediction, so the CTF measurement from last year has a W mass which is 8 sigma higher than the prediction of the standard model, then you know what you have to do in order to get agreement with experiment. For example, introduce a Higgs triplet with a suitably chosen vacuum expectation value such that it brings you into agreement with experimental data, or introduce SUSY particles or something else which break custodial symmetry in an additional way. Okay, so this ends our discussion of custodial symmetry and the tree-level row parameter and one of these additional miracles of the standard model. And in the afternoon we will continue with 3 generations of the standard model and discuss the CKM matrix. Okay, good. So see you then.